Welcome to my channel. I'd like to present to you my latest series on quantum field theory, which is the most mature form of quantum mechanics. In this series I want to examine quantum field theory in quite a bit of depth, but at the same time I want to keep it at a beginner's level. I call it a crash course. Well, let's examine the electroweak theory today. Now, the electroweak interaction is essentially electromagnetism, which is the most familiar force known to us, as well as gravity, combined with the less familiar force known as the weak force, which is involved in beta decay. So let's look at a bit of historical background. Now, the three individuals responsible for this electroweak unification were Steven Weinberg, Sheldon Glashow, and Abdus Salam. And the three were awarded the 1979 Nobel Prize in Physics. Now, what's important about quantum field theory is being able to explain physical phenomena in terms of equations. So what happens is when you go up and up, or when you extrapolate back and back to higher and higher energies, what happens is the four forces of nature, or at least the three that are describable as one, begin to behave as a single force. When you extrapolate back to about 10 to the 13th, 10 to the 14th giga-electron volts, otherwise known as GeV, the electromagnetism and the weak force begin to behave as a single force. If you extrapolate even back to about 10 to the, say, 15 GeV, the strong force and electroweak force begin to behave as one. And if you extrapolate even further back, about 10 to the 18th GeV, gravity begins to act, but we still don't have a quantum theory of gravity. We're still waiting on that. So today we're just going to focus on the electroweak interaction. Electroweak theory is formulated in this particular fashion: SU2 by U1, SU2 being a special unitary matrix. Special thing about special unitary matrices that make them special is that they have a determinant of 1 and a trace of 0, and we'll see what that is later. And U1, this is the component that represents electromagnetism. So what we're going to look at, spinors, which are important mathematical objects. We're going to look at the Dirac Lagrangian. We're going to look at leptons and their respective fields and their charges. We're going to explain what gauge fields are. Also going to look at the Weinberg Angle and spontaneous symmetry breaking. Okay, so let's get started. Okay, so let's start off with the concept of a spinor. So a spinor basically is a mathematical object, and you could essentially represent it in terms of two components. Here, the spinor is represented by a right component and left component, right? So now what we see here is that this is actually the Dirac matrices, right? This is called the Y5 matrix. Now we can represent the Y5 matrix in two ways: in this way and in this way. So what we're going to do now is we're actually going to pick the right-handed and left-handed components of the spinor. So what that involves is essentially taking if we go back here, so what we're going to do is we're going to take the right-handed component right here and the left-handed component of the field. So what we're going to do is we're going to take that and we're going to formulate it in terms of 1/2, because since we're dealing with both, we want to take the difference. So we deal with 1/2, put a minus sign. and then we essentially take both the respective fields. You can see that this represents essentially the right-handed, this is a left-handed spinor. Right-handed is essentially, it's got a positive one, and this has got a negative. It's pretty much the only difference between the fields. And then the resulting matrix we get is this, right? So, hence, what we have is, computing this out, so we get this matrix here, plot it out here, and just multiply it out, and respectively, when you multiply the terms by by the respective matrix, we get 0 for the right-handed, resulting in a 0, and we get just a 1 for the left, so we get a 1. So also we've got, for the right-handed, if we transpose the matrix, we actually get a value for 1, and we get a 0 for the left. So the take-home lesson from all of this is that we can compose a Dirac field in terms of right and left-handed components. So this is the next stage of our investigation of electroweak theory. This is the Lagrangian for the Dirac field. And what is a Lagrangian? Lagrangian is basically a mathematical equation or a relationship that employs the principle of least action, and we'll see what that means in a moment. So essentially, the Lagrangian, when we integrate the Lagrangian over time, we get the action of a system. So essentially, this is the Dirac Lagrangian. So you've got I, obviously square root of -1, which is an imaginary term. We've got psi bar, we'll see what that is in a second. We've got our gamma matrix with the power mu. We've got partial derivative mu. I think the mu is sort of cut off there. We'll finish that off. Mu, and we've got psi. So psi bar is psi transpose. Now, if you take a matrix and you transpose all the elements, so let's say psi is a matrix, for example, and we transpose all the elements, we get psi transpose. So, and now obviously the gamma matrix to 0. So that's essentially, so anything to 0 is essentially 1, so that's basically psi transpose. So let's see here. So essentially we get I, and we can obviously, we spoke about the right and left-handed spinors. So psi bar can now represent our spinors. Right. So we can expand that and put the two spinors. So the two psis here represent essentially spinors. So we put I, and then we put the right left-handed spinors, psi bar left, psi bar right. We expand that out, and then we go to the second psi here. We also expand that out, psi left, psi right, and then we can also expand that component, and we can have essentially we can have the components on their own as such. So what we can do is we can add L here for the right left-handed component, and then we can do the same, but in this case we can do it also for the right. So we're doing it in both cases, and then we just expand that out respectively. So that's the resulting Lagrangian for the Dirac field. Now, it's interesting to note that the last term actually goes away, it vanishes. Now, why does this happen? So as I said, when we take the difference of the two fields, we take the half and then we subtract the gamma matrix. So when we do that for the last term, which is here, we basically evaluate it, and then since we're multiplying out both 1/2 by each other, we get a 1/4. And then we can multiply these out, we get 1 minus y5 plus y5 minus, sorry, that's not y, that's a gamma. Apologies, that's a gamma, so that represents the gamma matrix. And essentially we get this result. But the important thing is this, because what happens is, there's another mistake here, it's meant to be a squared. So we have two gamma matrices here, squared. So these are the two gamma matrices multiplied by each other. We get the gamma matrix as a result. So we get the identity operator, or the identity matrix. So this last term actually vanishes. So this thing, so if I can represent this pictorially, this thing goes away because this is the identity operator. It's essentially repeating itself, so we can remove that, and then we're left with the resulting Dirac Lagrangian. Okay, so this is where the electroweak part gets in. So the Lagrangian for electroweak theory is quite long actually, but we can just represent the leptons. So a lepton is basically any elementary particle that's not involved in strong interactions. For example, electrons, muons, taus. So this is the Lagrangian, and we have part of the Lagrangian for the electron, muon, and the tau. These are our three leptons, which are involved in the electroweak interaction. So again, we can represent the electric field and its respective neutrino field as another matrix. And notice that we're only using a left-handed matrix. And why is that? Because the thing is that a left-handed electron, you can say, is virtually identical to a right-handed electron. And the neutrino here, neutrinos themselves have only been observed to be left-handed, so it's okay to just use a left-handed matrix. So again, we can apply for a right-handed electron for a left-handed electron, right-handed electron, we can apply the gamma matrix, and then we see as a result that there will only be a left-handed component of the neutrino field. So, and there's no actual right-handed component here, because this is meant to be for the neutrino, but the neutrino is missing. It says 0, so there's no right-handed neutrino, but we can have right-handed electron. So again, if you just refresh our memory, this is the Lagrangian that we derived before. But if you wanted to consider the full theory for the leptons, we can simply add the leptonic terms, but it's okay to just have the electrons there because they're virtually identical. Electrons are virtually identical to all the other leptons. So now I want to move on to the charges of the electroweak theory. So we're all familiar with electric charge. We can represent this as Q. Weak isospin is not very familiar. Now isospin, or isotopic charge as it was originally known, is basically it distinguishes particles that are very similar to each other. For example, like neutrons and protons. But those, this is kind of like to distinguish them. Isospin is sort of like a rotation in a fictional space. And we also got weak hypercharge. And we can relate all of these charges here relate to each other through the Gell-Mann-Nishijima relation, or the Gell-Mann-Nishijima formula. Okay, so Q, as we said, is electric charge. Sorry for the terrible handwriting. This is isospin, more particularly it's the third component. Of the isospin. And Y is your weak hypercharge. Okay? So that's just basically a brief look at the charges. So now I want to look at a bit of group theory, and we're going to look at the unitary transformations of the electroweak interaction. So as we said, the electroweak theory is formulated in terms of SU2 times U1. SU2 is basically a non-abelian group. U1 is abelian. So as a result of SU2, we can get 3 gauge bosons, W1, W2, W3. We got the subscript mu for each. And U1 just gives rise to a single field. And that field is associated with the electromagnetic force. So now we can derive the Lagrangian for electroweak theory, incorporating both leptons and the gauge bosons, or the gauge fields. So what we can see here is that if you take a right-handed spinor, perform a gauge or a unitary transformation on it, it's essentially indistinguishable. That we get an exponential times times I beta, and then we get the right-handed spinor. So it's virtually indistinguishable. And so is the Lagrangian. Lagrangian has a symmetry. The Lagrangian is invariant under these transformations. So, but the thing is that the left-handed case is actually the left-handed case itself is not actually symmetrical, because if we go back to our charges, the weak hypercharge of the left-handed field is actually -2, but the weak hypercharge for right-handed. So for a right-handed weak hypercharge, the field has a value of -2. For a right-handed one, it's -1. So we have a difference of 1/2. So for the L, for the left-handed spinor, all we need to do is put that over 2, since the difference is 1/2. And we can put that as a matrix. So you got your electron neutrino, right-hand electron, left-hand electron, and you could essentially perform the gauge transformation. So respectively, this goes here, here, here. We just act on those using the particles. And now we can actually define the field strength tensor F mu nu, and you just take the partial derivative, and we take the B field, which is here, and we put it as a product of the B minus the partial derivative V. And what we can actually do is we can put the Lagrangian for that B field as -1/2 F mu nu, F mu nu. F mu nu is the electromagnetic, or the Maxwell tensor. And we want to ensure that this term is covariant. So in other words, we want to ensure the term is invariant under Lorentz transformations, which comes in special relativity. So what we are going to do is introduce a covariant derivative with a coupling constant BGB. So these are, if you're not familiar with these are your Pauli matrices. This is sigma x, sigma y, sigma z. Here we'll just call them tau 1, tau 2, tau 3. And your standard SU2 transformation is essentially an exponential I upon A, and J. J is just the iso representing coordinate or position in the isospin space. So again, right-handed spinor is symmetrical under that transformation, but the left-handed spinor as well, because we mentioned it differs by 1/2, we need to put it over 2. So now we can essentially perform the transformation again, this time in terms of the SU2 transformation. So again, you multiply that out into the respective position, and you get this. You apply the particles, and now we have to take the trace. So the trace of that gives us a -1/8 when you actually take the trace of that matrix. Okay, so this is where it gets this is where it gets pretty essential. So we need to again keep the derivative covariant, like I explained before. So what we're going to do is we're going to introduce IGW in addition to IGB. These are both coupling constants. We're going to relate these two coupling constants in terms of the Weinberg angle a little bit later. So simply put it, you got IGW tau over 2 by W mu. That essentially means we're taking IGW over 2, and then we're taking all of the successive tau 1, tau 2, tau 3 terms after that. So since we want to make the derivative covariant, just apply that to the derivative from the Lagrangian that we derived before. So just take this derivative here, place the covariant term, place the covariant term just in front of it right here. So these, just put it in front here. So yeah, and now we can. So now the essential thing here is that the right-handed field itself doesn't actually interact in the interaction that involves a weak isospin. That's why here in R, you don't actually see GB over 2, because it's interesting here you see GB over 2, IGW, tau over 2, right? And this is for, remember, this is for the left-handed field. This is the right-handed field, right? But why don't we see this term also here? And that's simply because the right-handed leptonic field does not interact in any interactions involving weak isospin. So we simply don't have to add that into the Lagrangian. Okay, so now we have the Lagrangian for the leptonic field simply, with the right-handed, left-handed components, with the covariant derivative to maintain covariance. So as I said before, right-handed only does not interact with weak isospin. We don't need to put that, so only put the GB coupling constant. For the left, we put both coupling constants in the covariant derivative. So now we can put what we derived earlier. So essentially, we can put this term here in accordance with the other terms. So we have the total Lagrangian of the Electroweak theory, which includes the leptons and the gauge fields, as the right-handed field, as I mentioned, plus the covariant derivative, the left-handed field plus its respective left-handed field plus its respective covariant derivatives, and then we just add the gauge fields here with the trace element and the electromagnetic tensor. So far, so good. Now comes the interesting part. The interesting thing is that there's a special condition in quantum field theory called the Goldstone theorem. Now, the thing about the Goldstone theorem is it actually demands that in any manifestly Lorentz invariant theory, particles have to be massless. So we have to evade that theorem. So how do we do that? We got to break the symmetry. So essentially, you got here. So the Higgs field we can represent as phi, which is here, right? And we can express that in terms of a two-component field, phi A, phi B. Phi A equals phi 3. So it's essentially a four-component field, right? So we can represent phi A as phi 3 plus I phi 4 and over root 2. It's essentially to maintain over root 2, so the function normalizes. So basically, so it's really composed of four fields, 1, 2, 3, and 4, and we see that if you multiply out this by its transpose, we get 1/2 plus the respective terms after that. So let's now we can actually use a form of the Higgs field. Let's use one form of the Higgs field by setting A to 0 and setting B to phi B to phi 0 plus Hx over Hx over root 2, and essentially the Hx term just represents a sort of like a function in the space. It doesn't really represent any real number. So okay, so this is basically the form of the Higgs field that we have now. Okay, so now I want to look at the Dirac Lagrangians. This was the Lagrangian that we derived earlier, but there's something different here. I've added something extra. What is this? This is a minus m psi bar left psi right plus psi bar right psi left. So what is this? This is the mass term. So I've added a mass term. So I've added a mass term to the Lagrangian, and m here is just a number. It's just a scalar number. And when you actually take the interaction of the Higgs field with the actual leptonic and the gauge fields, this G term pops up. This GE term is called the Yukawa coupling. The Yukawa coupling actually, it actually gives you an idea of how strongly the Higgs field couples with the matter field. So now we can look at essentially each term. We have our we have essentially so we've got psi bar left, phi. So we've got both particles here. We've got both leptons, left-handed electron, left-handed neutrino. We dedicate to each one component of the Higgs field. Thus we have the electron neutrino coupled with the Higgs field, and the left-handed electron coupled with the second component of the Higgs field. So now we can essentially expand that out, so we can put both components as such. And remember, we set phi a to 0, so the neutrino term drops. Thus, the electron term is left, and we act on it with what we set b to. We set b, remember, to phi 0 plus hx over root 2. So essentially, using if we define a right-handed spinor as such, we get essentially the same result. So, okay, as such, we can see that if you act upon the Lagrangian with the mass term, the electron itself gets a mass. And you can essentially represent the Yukawa coupling of the Higgs field to electron field by putting essentially left-handed electron, right-handed electron plus the bar respectively, and then essentially subtract that out from the mass term, because if you remember, we have to have a minus m. Here the negative GE plus the hx of root 2 plus such is representing the mass term, and that essentially leaves us with the mass of the electron. This is the mass of the electron. Right. So this is essentially, so what's happened now is we've broken the electroweak symmetry, but there's a problem. We've predicted that an electron has a mass of GE phi 0, but we've also predicted, if you had noticed, that the neutrino has a mass of 0. This is a problem because this is actually wrong. Neutrinos don't have masses of 0. They have very small yet non-zero masses. In fact, there's a very good way of proving it using neutrino oscillations, but I won't even get into that. The essential thing here is that this result here, a massless neutrino and a massive electron, shows that the Electroweak theory, or at least the Weinberg-Salam model, is incomplete. Okay, so now let's move on to the gauge bosons, the W boson and the Z boson. These are the particles involved in the weak force. So how are we going to give them mass? Again, we have to break the symmetry. So since the symmetry requires them to be, why do we have to break the symmetry? Because the symmetry requires that they have no mass. So in order to get rid of that condition, we need to break the symmetry. So essentially what we have here is, again, if you go back some slides, essentially we represented the Higgs field in terms of two components, if you can recall. Okay, and we had the four components as such. This time, instead of phi, since we're dealing with the W and Z bosons, just have them as W's and Z's. So if you go back to our picture here, so at the moment we're just dealing with the W particles. So as I said, Higgs field, four complex components, and then again we have to make the derivative covariant. So we just apply that derivative to the Higgs field, again with the two coupling constants G of B and G of W, and I'm going to show you in a minute how we can relate those two coupling constants using the Weinberg Angle. And we just again apply that to the Higgs field. So now it's essential to see, if you go back here, so you've got tau with sort of like an arrow bar on top. This shows that we're including tau and all of the rest of its components. Now what are those components of tau? So we got tau here, we got tau 1, tau 2, tau 3. What did we say tau 1, 2 and 3 were? They were the Pauli matrices, which represent the SU2, sorry, write it here, clearer, SU2 symmetry, right? So now we just apply those to the W particles. If we multiply those out, we get a W3 mu, and then we get, for the next term, we get essentially a W1 mu plus an I W2 mu, and a negative W3 mu, and a W1 mu minus I W2 mu. So you're wondering what that is? It's basically we're just multiplying the terms out to the leading terms. So we're essentially figuring out the product, and this is the result that we get. Therefore, okay. So we can now get the derivative of the. Wait a minute. Okay, we can get the derivative. We can get. So essentially, we can get the derivative of the field, which is here. Now, if you're wondering, if you're not familiar with these particular derivatives, these are partial derivatives. Normal derivatives are just with respect to a single variable. Partial derivatives are employed when you have more than one variable. So we have here your partial derivative. We take the derivative of the field, like we defined before. Essentially, we get it 1/2, and you get the partial derivative mu to the h. So again, we can plug that into the Higgs. I'm not going to call it Lagrangian, but just call it the formula for now. Plug that in, add the coupling constants, add the two, essentially the two products that we got earlier, plus the second coupling constant GB, and add the component of the Higgs field. So now we just expand that out. We find that essentially this term here comes as a result of multiplying out the covariant derivatives by each other. So essentially, when we multiply that product that we got earlier by the actual Higgs field, we get covariant. We get the coupling constant over 2 by I multiplied by that. So now, what I want to do now is actually get the masses for the particles. So we take d mu phi dagger, where dagger represents the matrix being transposed, and then we so essentially this is what d mu phi dagger is. The only difference from the original Lagrangian is that instead of a plus sign, we're just minusing each of the terms. And now when we actually multiply that out, we multiply out d mu phi dagger by the original d mu phi, we get this result here. So how do you get that? Essentially what we did was multiply this term here by that same term here, right? And the result that we got was this, right? So now we want to multiply the next term. So we want to multiply this, just multiply this term here by the original term. So we get essentially this, so multiplying that from the original and then that by the transposed, we get essentially essentially the same result, but this time with a plus sign. We also have a cross term. What a cross term means is that we've got an equivalent way of writing this, an equivalent way of dealing with this. So when you take the cross term, we get the two coupling constants multiplied by each other, this time over 4, right? And then we get a second cross term where we can just multiply that coupling constant over 2 by I by the Higgs field being applied to the W particles, and then we essentially get a similar result, except the B and the W are just switched over. That doesn't really make any difference. So now essentially this is the final quadratic term that we are concerned with. The coupling constant GBQ over 4 B mu by B mu, and then that's basically your Higgs field again. So now we're getting up to the Weinberg angle. The Weinberg angle was named after Steven Weinberg, as we mentioned earlier. So we can, okay, so when the symmetry is broken, there's a particular angle by which the group, the SU2 by U1 rotates the symmetry group. So we can represent that by multiplying, by taking, for example, B mu. Yeah, let's take one example. Multiply that out, you can then multiply A by cos of the Weinberg angle, and then essentially you can get a minus Z, essentially. You can do that for and we get this result. So we get B mu equals A mu cos by the Weinberg angle minus C mu sine of the Weinberg angle. And then we do the same thing essentially for the W particle. So we take that, multiply it out by A, multiply that out by sine, and then multiply that out by cosine, and then we get essentially this, pretty much we get the second term. So so I've written here that keep in mind the only leading term, so we only need this term here, that's the leading term, because that contains the scalar number. So when we do that, when we apply that, we find that when we go back to the result that we got from before. So for example, we got this first coupling constants. We go back and we just multiply that out by the W plus W minus particles, and then interestingly we have to add another term, because instead of the W3s, all we need to do is now add the respective Weinberg angles and then multiply that by the Higgs field squared. And we do that, we just multiply that out for the rest of the particles. We take the cross terms. I'm not going to go through this, it's quite tedious. And then now we have to look for a mass. How do we find a mass? Okay, so essentially what happens now is, so we have to look for a mass. So if we look here, if you've done multiplying yourself, we get the mass. So we get A mu and A mu terms here. So that is how we're going to look for the mass. So we look for the mass by removing those A mu terms, separating it, bracket or brace, and then you put that essentially as you put all the coupling constants that we got from all the cross terms. And then that's because we have negative GBW over 4 and negative WBG over 4. These are essentially the same terms. So that becomes essentially, so minus 4. So essentially that becomes G and then minus GBW over 2. We get this. So now we can hopefully get a mass. But we can get a mass for the photon. Because what happens here is that from this diagram we see that if we do a little bit of high school trigonometry here, this is your hypotenuse, opposite, and your adjacent, your right angle here. So you see cosine, which is adjacent over hypotenuse, essentially is your coupling constant GW over the G squared B plus the square root of G squared B plus G squared W. So and essentially get a similar result for sine. And essentially we can now replace these cosines, which we got previously here, these sines and cosines. We can replace them with these Weinberg angles. You introduce them into the equation. When you evaluate it, it turns out that the photon, in other words the particle which is responsible for light, is actually massless. And this is a huge success. We've actually done a calculation now that agrees with the experiment. we've found how you can break the symmetry, make the electron massive, but at the same time keep the photon massless. The photon has zero mass. Now this is a good result. So now let's find the masses for the rest of the particles, more particularly the Z, W bosons. So if we go back, take the coupling constants again, and then we plug these terms back in, we get for those essentially, we get essentially, so we're replacing these sines and cosines, and we're replacing them by these terms here. Bit messy. Here. And now we get this result here. So this actually tells us that, because this is squared, we want to get rid of the squared, so what we got to do is sort of square root it, and the result is we get is this. Now this is essentially the mass of the Z particle. So what we've done now is we've broken the symmetry, the SU2 times S times U1 symmetry. We've given the electron a mass, we've kept the photon massless, and we've given the Z particle and the W particle a mass. And we can see here from the Weinberg angle that we calculated, there's a set of theoretical bounds on the mass. So if you take the coupling constants, put them over 2 with the Higgs field, and then evaluate that over the Weinberg angle, we get a theoretical bound for the W particle. We can get a mass of more than or equal to 38 GeV, where GeV is giga-electron-volts. For the Z particle, we can get a theoretical bound of greater than or equal to 76 giga-electron-volts. Pretty heavy particles. Thank you very much for listening, and do subscribe. I am looking forward to your feedback and comments. Thank you very much for taking time to watch the video. If you have any questions, please do leave them in the comment section, and stay tuned for future videos on quantum field theory. Thank you very much.